Hello, and thank you for joining. My name is Yanni Shafkalis, and I'll be your host in discussing a new way to evaluate, tune, and rate an audio system's performance, specifically in a vehicle. In the world of automotive audio testing, there has traditionally been very little agreement and standardization around the equipment and methods to use and targets to aim for. This session will illustrate the benefits of using a 6-microphone array, referred to as the Christmas tree, for objective measurements while also demonstrating the limitations in terms of audio quality assessment. This is where binaural measurements and advanced quality predictors like MDAQS come into play to allow us a better and more accurate way of evaluating the quality of a device's playback performance. Let's take a look at the Christmas tree, since this is what most companies are using. The Christmas tree is conducted using 6 microphones. The underlying principle being you get 3 sets of ears at different driver sizes, 5th percentile, 50th percentile, and 95th percentile. And with one measurement, you can take advantage of spatial averaging. Having an array that covers average head sizes is great, and for automotive applications, we tend to have a very well-defined head placement, close to the headrest, that can help guide the positioning of the array. Measurements must be conducted in the driver's seat with a recommendation to also measure the other seating positions. And generally, we'll want to conduct our measurements with all sound system user controls like faders, equalizers, etc., set to default. Depending on who you talk to, the types of measurements and data you could capture varies. Currently, there's a technical committee in the AES that recommends you look at 3 primary measurements. Frequency response. This is the most common measurement in all of audio, not just automotive. It reveals basic properties of the system and can provide a visual indicator of spectral balance in the audio system. Max SPL. This is an important system-level spec that puts demand on the loudspeakers, amplifiers, and system as a whole. Impulse distortion, buzz, squeak, and rattle. The idea is to uncover artifacts that the human ear would sense, which wouldn't necessarily be picked up by the frequency response measurement. The goal is to focus on a full system measurement and on the most basic attributes that are widely used in the industry. This could allow for easy vehicle comparisons. From a measurement setup perspective, we'll want to create a hardware configuration in Aqua that allows us to capture our 6 microphone signals. We can do that in a few different ways, depending on how our LabCore is equipped. We'll assume that our LabCore has a single core-in ICP card and a core-in A2 card that can handle a combined 6 channels of ICP. Generally, ICP mics are going to be the easiest to work with due to the cabling only needing to be a 2-wire construction as opposed to the thicker and heavier 7-wire construction found in limos. We strongly recommend 1/4-inch microphones for this type of work since we're working with potentially diffuse sound fields and wanting to capture sound up to 20 kHz. The 1/4-inch mics are smaller than 1/2-inch mics and therefore have less influence on the sound field they're in. Before we share some measurements, one last comment about stimulus material. We've often found it recommended that people use pink noise or sine chirps. Both of these can present serious issues in modern audio systems that employ sophisticated signal processing in smart amplifiers, such that the data we measure could be invalid. At Head Acoustics, we're always proponents of using real speech or music signals as stimuli, since it puts the audio system in a real-world condition and use case. With that being said, let's take a look at some measurements from the Christmas tree. Let's start with frequency response measurements. With the 6-mic array, we capture 6 channels at once and of course correct for the spectral shape of our stimulus, in this case a log chirp, so we can see the transfer function of the car audio system for the driver's seat position. This gives us an indication of the audio system performance and something we can compare against other vehicles or other seat positions. To the right of that graph is the same measurement but taken from the passenger seat location. However, because we're using a log chirp and we transmitted this over Bluetooth, can we be sure that the audio system treated our stimulus file correctly? What if we had transmitted it via a USB thumb drive or a CD? A file in a head unit perhaps, or auxiliary input? If these options even existed. For distortion measurements, we can resort to the good old total harmonic distortion or THD plus noise measurements, as they are as fundamental to audio engineers as frequency response measurements. We'll want to capture the distortion artifacts for all frequencies, so if the system permits, we can apply a stepped sine or a farina sweep to document the distortion of the audio playback system. The bottom two graphs show us the distortion across the whole frequency range for both seat locations. This depicts the distortion products for each frequency component and lists their ratio in dB. 20 dB equals 10% distortion, 40 dB equals 1% distortion. So if we compare the two graphs of the driver's position and the co-driver, the passenger position, we don't really see too much of a difference. But even if we were to compare them, what does that tell us about the vehicles? Sure, we can see which seat position or which vehicle has more THD, but what is going to be perceptually relevant? And yes, we can see the frequency response changes, but is there a single target curve that we should be aiming for? If yes, then presumably we've already hit the pinnacle of audio engineering in one vehicle somewhere, and we should just have all cars match that. If not, what meaningful tuning decisions do we make based on this? Or as a consumer, which vehicle audio system would you prefer? Let's take a look at MDAQS. If you're new to MDAQS and the research behind it, we have an application note in 2 other webinars. One webinar discusses the fundamentals of the research hosted by the lead researcher Magnus, and the other webinar focusing on the practicality of MDAQS in automotive. If you haven't checked these out yet, we suggest you do. The links to our other webinars and app notes were emailed. If you haven't received them, please reach out and we'll get them to you immediately. While we go dance through the topics of MDAQS, let's take an MDAQS measurement and calculate the results. Place the super HMS in the car, connect to the head unit, send the signal, and calculate. So what is MDAQS specifically from a high level? It's a cutting-edge audio playback assessment technique. It simplifies audio quality characterization to 3 mean opinion scores, can be applied to almost any acoustic playback system, and is a panel of virtual listeners producing consistent and repeatable audio assessment results. Now let's get to the MDAQS dimensions. The short story is that MDAQS is a sophisticated algorithm that stimulates human perception as it relates to audio quality. One of the revelations discovered in the MDAQS research is that the general consumer will evaluate overall quality along 3 dimensions: timbre, distortion, and immersion. Combining, calculating, and weighing the 3 ratings differently brings us to MOS-O, the overall score of how the system performs. With the Christmas tree, there were recommendations to measure frequency response and distortion elements, but does that accurately account for human perception? And does a 6-mic array look like a human head with ears? Far from it. In trying to deconstruct MDAQS, we tried some common and more conventional parameters to compare back to. For timbre, we have frequency response and consistency, level versus time. For distortion, we looked at total harmonic distortion plus noise, and signal-to-noise ratio. For immersiveness, we have intraoral level differences, intraoral time differences, and frequency response tightness between 2K and 4K. Oh, wait, MDAQS is done. Let's take a look at the results. Here are the MDAQS scores for one of the vehicles we tested, a premium electric SUV. We tested this vehicle in all seat positions, but for now, we'll focus only on seat position 1, the driver. MDAQS rates from 1 to 5, 1 being the worst, 5 being the best. If we take a look at the furthest bar on our graph, our MOS-O, the overall evaluation, is relatively high, sitting at 4.1. It's crystal clear what the average consumer would think of this audio system. They would rate it a 4.1 out of 5. Now let's take a look at the entire vehicle in all of its seat positions. This vehicle had some pretty impressive scores compared to others we've tested. Let's take a look at the overall scores, just MOS-O. It's interesting that seat position 1, the driver's seat, scored the worst amongst all 5 positions, sitting at 4.1. In this vehicle, seat position 2, the passenger, scored the best. But let's see how this shakes up against the other 3 vehicles we measured. When we tune a vehicle, we typically aim for seat position 1, the driver, or seat position 4, the center of the cabin, to be the best performing. From the results, only one vehicle proves that to be true, the premium SUV. In our midsize SUV and premium electric SUV, interestingly enough, the favorable position is seat 2 in the front row and seats 4 and 5 in the second row. This puts an emphasis on better audio quality on the right side, the passenger side of the vehicle. I'm sure this wasn't by design. But the minivan switched from left in the front row to right in the second and third rows. I'd venture to guess this was a consequence of subjective and unrepeatable measurements. Audio quality is so much more than considering only frequency response. Distortion and spatial components tell the other parts of the story. That's why we're big believers in MDAQS being a tool that can help speed up the tuning process for automotive audio systems. It immediately tells us what the audio quality prediction of a particular setup is going to be, along with giving us indications along the 3 dimensions for what we can improve on. So the question is, where do we draw the line in the sand? The line in the sand is MDAQS. With the lab core, we can support Christmas tree measurements so you can capture data the way the industry has done for decades, but adding MDAQS to the tool belt gives us a large pool of virtual listeners to rely on. After careful analysis and tuning using the Christmas tree and MDAQS, we can deliver a ready system for final voicing and branding by the expert golden ears. Thank you. If you have any questions, please feel free to reach out to your account manager or to our general inbox, support-na@headacoustics.com.